Hi, everybody. So let's talk electron configurations. You got a little bit of an introduction to these in your homework assignment. Kind of described like what an electron configuration was, what an orbital was, the different shapes of orbitals, all that kind of stuff. And this is going to be like taking all that information you learned, just like reinforcing it for you and putting it down in one place in your notes packet so you have easy access to it. So let's start by thinking about electron organization. Where are these electrons that exist within an atom? We know that inside the nucleus, you've got your protons and your neutrons. And then from Schrodinger's model, the quantum mechanical model, our most updated model of the atom, we know that electrons don't actually exist in those little energy level rings that Bohr drew in his models. Instead, electrons exist in a cloud outside the nucleus of the atom. We learned from the quantum mechanical model that we can't actually know where an electron is for sure going to be, right? But we can predict high probability of finding those electrons in certain regions, and those certain regions are called orbitals. So an orbital is a region of space. And I'm talking like a physical region, like it actually exists, right? It's a region of space where we have a high probability of finding electrons. So you can think of an orbital like a room, like your room in your home. This is your kind of space, right? It's where you are very likely to reside. If you're hungry, you can go out of your room and go to the kitchen. Like you're able to wander around your house, but you're very likely going to spend a lot of time in your individual room. So there's 4 different types of orbitals that you learned about. We're only going to really work with 3 of them. Orbitals are named after letters. Lowercase letters are what we use. We got S, P, D, and F. Each individual orbital itself can only hold 2 electrons. Each of the orbitals also has a different shape. So you can see a picture of the S and P orbitals here. Keep in mind this is a region of like 3-dimensional physical space. So when you see the S, it's actually like a spherical shape. The P orbitals, these are trying to show you with the X, Z, and Y in which direction they're oriented in 3-dimensional space. So I'm going to draw you a little bit, let's do it over here, a little picture. So when you're drawing in 3-dimensional space, you've got your axes that kind of look like this. You've got your x-axis that's going to come out towards you, your y-axis that's going in line with the plane, and your z-axis that's going up. So this can be changed and manipulated and oriented completely differently. If you just turn it, it doesn't really matter. But you're always going to have 2 axes that are in the planes, one going up and down, one going side to side, and the other one coming out at you and going away from you into the plane. So these orbitals are oriented along these axes. One goes up and down. Just for simplicity, I did not draw the full axis here, but it would look like this. And then you can draw a dashed line to show it's going into this page away from you. And then Y follows along that plane right there. And then X, this would come out towards you. So I'm going to kind of bold it if I can. This comes out towards you. And then the other half of the orbital goes away from you back into the paper. So these orbitals exist at this like little center point here. This is where they would connect. They're just separated out here to show you the different shape of them, showing that they orient themselves into the 3-dimensional plane, right? Okay, so that's what an orbital is. Holds 2 electrons. They each have different shape. There's 4 types of them. Then you have sublevels. So don't overthink a sublevel. What a sublevel really is it contains multiple orbitals, each with equivalent energy. So you can think of this like your bed in your room in your home. So let's say that you are an only child. You have your own bedroom. Ooh, lucky you, I guess. You are just like an S sublevel, an S orbital. There's one bed for one person. You're going to sleep in it in your room. But let's say you have to share a room with 2 of your siblings. Each of you needs to fit, each of you needs your own space, your own bed inside your room. That's kind of like what a sublevel is. You would have something like a P, Px, Py, Pz. It's 3 regions of space, each where electrons can reside, but they're all in the same orbital. They're all in the same level, right? So they all have equivalent energy. You all live in the same room. You all have a bed in that room. You all have equivalent energy. For the purpose of this, we need to make sure, just for my analogy to work out, when I say equivalent energy, it would mean like you don't have bunk beds, right? Each of you has your own separated bed within the room, but it's not like a bunk bed. Because if you had a bunk bed, one of you has to climb up into the bed, one of you gets the downstairs. That's not equivalent energy. That one person's doing all the work every night, right? So sublevel, multiple orbitals, each they have equivalent energy. This really comes into play when you're talking about P, D, and F sublevels where they have multiple orbitals that are inside. S is a little bit different. Anytime you have an S orbital or an S sublevel, it only contains one of those individual spherical orbitals. S stands alone. So if S has one orbital inside of it, how many electrons can each orbital hold? They can hold 2. So an S sublevel can hold a maximum of 2 electrons. Now think about 3. So P's come in 3s. A P contains 3 orbitals, each with equivalent energy. So 3 orbitals, each orbital can hold a maximum of 2 electrons. So total, the P sublevel can hold a maximum of 6 electrons. Each orbital holds 2. Then you have D. D sublevels contain 5 orbitals total. So if I double that, because there's 2 electrons that can fit in each orbital, I get 10 electrons total in the sublevel. And for F, it's got 7 orbitals, so I can hold a maximum of 14 electrons. Okay, so let's kind of compare this to the Bohr model. See how it matches up, right? So I have argon here. The blue dots are representing electrons that would be in an s orbital, and then the green dots are representing electrons that would be in a p orbital. So remember we said that one of the things that Bohr got right is that electrons do exist with a certain quanta of energy, right? They have a certain amount of energy associated with them. So if I take a look at n equals 1, that very first energy level closest to the nucleus, I notice there's only 2 electrons in it. Both of those electrons exist in an s orbital. So when we started learning about Bohr models, we said, oh, n equals 1 can only have 2 electrons in it. And this is why. In the first energy level, the only sublevel that exists is s. There's only 1 orbital in that s sublevel. And so the total electrons that can fit in that energy level are 2, because this number times 2 will get me the total electrons that can fit in there. So this is why for the Bohr model, only 2 electrons fill in n equals 1, because in n equals 1, that first energy level, the only orbital that exists is s. In n equals 2, the next energy level up, we said we can fit a maximum of 8 electrons. In n equals 2, we can see that there is an s orbital again, but there's also a p orbital that exists. I'm going to highlight here. These are the electrons that are in my p orbital. One of these would be px, one would be py, one would be pz, and then these would be in the s orbital. So the total orbitals that are in the energy level, there's 4 of them. There's 3. I'm going to actually break this up so I can show it. There's 3 that are coming from P, and there's 1 that's coming from S. So how many electrons total can fit in there in n equals 2? 8. It's the exact same thing that we're seeing for n equals 3. I have 2, 4, 6 electrons in p orbitals, 2 electrons in an s orbital. So I'm just going to copy this entire portion of the table because it matches up directly. So remember we said that the Bohr model was really only accurate up until atomic number 18, up until argon, and that's because after the this third energy level, or in the third energy level, there is also a d orbital. There happens to be a d orbital in there, which means that if we're saying for the Bohr model only 8 electrons max can fit in each level, it's not actually true, because the third energy level holds our first d orbital, and then the fourth energy level holds our first f orbital. So there are, in fact, more electrons that can fit in these energy levels. Okay, so because of the rules for filling Bohr models, because of the rules for electron level filling, Bohr models are only accurate up to atomic number 18, which is argon. So we need another way to model electron locations. So for this, we're going to use our electron configurations. Since the Bohr models didn't work, we need something that does obey like this quantum mechanical model of putting electrons in these energy levels, in these orbitals, these areas of space. So how do we do this? You learned about these little babies last night, or whenever you decided to do your homework. These are called ground state orbital diagrams. Orbital diagrams are like... they're ways of representing locations of electrons by representing orbitals as like little boxes, as like little areas of space. So the first thing you need to figure out when drawing an orbital diagram or when writing an electron configuration is you need to know how many electrons you're actually dealing with, how many are present in the atom. So how do we figure that out? Well, we always assume that electrons are neutral unless otherwise stated. So if they're neutral, it means they have no charge. Their positive and their negative charges cancel out. So if I wanted to figure out how many electrons are in the atom, I need to find atomic number by finding atomic number, which again we represent as capital letter Z. So once I find the number of protons, I know my number of electrons should be equal and opposite to that so that they cancel out. Then there's a couple of different rules you learned for drawing ground state orbital diagrams. The first thing you want to do to get yourself set up is draw yourself like a blank orbital diagram, a little template. So this is showing you a blank orbital diagram that would fill up to the 3p orbital. You will see examples of this that I'll show you in class of if we needed to go larger, like if we needed to fill into the d orbital. And I'll show you how to do those. But for now, let's keep it simple since we're just learning these. So you draw your blank orbital diagram, get yourself set up with your little template, and now you need to figure out where are my electrons going to go, how are they going to fill. So there's some 3 rules that you learned about that teach you about how electrons fill into the energy levels of an atom. The first is the most important. That's the Aufbau principle. What this says is that electrons will always fill in order of increasing energy. The reason why this is important is because everything in the universe is designed to be lazy. It wants to exist in the lowest possible energy state that it can. So if I'm going to be an electron that fills into an atom, I want to be as close to the nucleus as I can, be as close to those protons as I possibly can, so I feel that lovely force of attraction between me, my negative electron, and the positive charge of the nucleus, right? So you're always going to fill from low energy to high energy, meaning n equals 1 to n equals 2 to n equals 3, until that energy level is full. So we represent electrons by using up and down arrows. You'll often see me represent them as like half arrows like this, just to make our like diagrams a little bit easier. But if you draw out full arrows, totally fine. I just want to warn you, that's what mine often look like. So this is showing you where our electrons will fill into the energy levels. They start at the low energy level, 1s, then they fill up. Then come Hund's rule. So Hund's rule states that if your electrons are in the same sublevel, meaning they're all in P, they're all in D, they're all in F, they're not going to pair up in an orbital until they have no other option. So think about this, right? Like if you go on vacation with your family and you and your sibling get put into the exact same room and there's 2 beds in the room, why are you going to want to share a bed with your sibling rather than each of you taking your own bed, right? You want to spread yourselves out as far from each other as you possibly can. It just makes the most sense. That's the same like truth for electrons, right? And you can also think of it because, or you can also think of this reason why, because it should make a lot of sense to you. Electrons carry their own negative charge, right? If you have a negative electron and it tries to get into bed with another negative electron, they're going to feel a lot of repulsion. That's not going to be favorable for them. That puts them in a higher energy state than where they'd like to be, right? So this would be for like, let's say I'm in the 2p orbital, I would fill one electron in one orbital first, then a second electron in the next orbital, and a third electron in the last orbital before I decided to pair them up, and then they had to share an orbital, or they had to share a bed, right? So that's Hund's rule. The last one is Pauli exclusion principle, which I just kind of naturally started doing as I was filling these. Pauli exclusion principle says that electrons that exist in the same orbital must have opposite spin sign. So you draw one arrow up and one arrow down. It's like if you had to sleep in the same bed as your sibling, like, are you sleeping head to foot or head to head? Like, how are you sleeping? Well, electrons like to sleep one spin up, one spin down. This puts them kind of as far away from each other as they possibly can. Don't really worry about what spin means just yet. You don't need to know it for this class. And then lastly, count up your electrons. Just double check, make sure you have the total electrons in your diagram that adds up to the total amount of electrons you wanted for the atom. So like if your electron diagram is supposed to have 18 electrons, make sure you have 18 electrons. Okay, you can pause the video here and practice drawing the ground state orbital diagram for carbon, and then come on back and check your answer with what I got, okay? Okay. All right, so hopefully you paused the video, hopefully you ran this out. Carbon has an atomic number of 6, which means it's got 6 electrons that it needs to fill in its ground state orbital diagram, so this is what the orbital diagram would look like. Make sure that your electrons in the 2p sublevel are separated from each other according to Hund's rule. Okay, so next up. How do I then write an electron configuration? This is easiest to do after you've drawn your orbital diagram, because an electron configuration is essentially like taking the orbital diagram and like collapsing it, like taking it and writing it as a line all in one order, like taking the boxes out, just like you like you were pulling things off of a shelf and then everything started collapsing, right? That's exactly what an orbital diagram is to making an electron configuration. So energy levels are represented by whole numbers, right? 1, 2, 3. Your sublevels are represented by your letters, S, P, D, F. And then your number of electrons is represented as a superscript, as an exponent. Total number of electrons in the orbital, that's how many electrons you put as your superscript. So for carbon, I start with my lowest energy level, which is 1s. I notice that I put 2 electrons into the 1s orbital, so I write that orbital's configuration as 1s2. So this tells me I have 2 electrons in an s orbital. That's the first energy level, 1s2. Then I just keep going up from there. Well, I put electrons next into 2s2, or into 2s, and I put 2 of them there. Next, I have the 2p orbital. So I'm still in that second energy level, right? So the second energy level, next I filled into a p orbital, and I put 2 electrons in it. Okay, I'm going to talk to you more about this in class, but one thing that you can kind of start noticing is I had you label on your personal periodic table the blocks of the periodic table, right? So your blocks on the periodic table, let me zoom out and go to this page here, are kind of labeled this way. So this is your S block, your first 2 groups on the periodic table. This is the P block, the last 6 groups on the periodic table. This is your D block, your transition metals. That's these 10 elements on the periodic table. And then lastly, your F block down at the bottom, these lower 2 groups of elements. So carbon shows up right here on the periodic table. What we just wrote was its electron configuration. The electron configuration was 1s2, 2s2, 2p6. Here's what's really cool. This is showing you not only where the electrons reside within the atom, it also shows you where it exists on the periodic table. Oh my God, that's so exciting. What? Blowing minds. So take a look at this. 1s2, 2s2, 2p6. This last term of any electron configuration will tell you where the element that's under study exists on the periodic table. This tells you the energy level. This tells you the last electrons exist in the second energy level. This corresponds to your period. Period 1, period 2, period 3, period 4, 5, 6, 7. Okay, so second period, putting us right here. This tells us, the orbital letter tells us which block it's on the periodic table. This is the P block. This is the P block. This is where carbon lives, in the P block. And then, wait, hold on. This isn't the electron configuration for carbon. LOL. 2p2. That would have been crazy if I just did this whole thing and I was like, 2p6. And I was like, yeah, it lives here. And then I was totally wrong. Oh, gotta check my work, guys. Okay, so 2, second energy level, P block, 2, number of electrons that exist in that p orbital. This tells you how many elements in it is to that block. So 2 electrons, 2 elements in. First element, second element. 2p2. Second energy level, P block, 1, 2 elements in. That's where carbon lives on the periodic table. What? Crazy. So cool. Okay, so here's what I want you to do. I want you to get some practice drawing ground state orbital diagrams and writing electron configurations. You're going to do these for these 3 practice problems, and then you're going to check in with the answer key, notes packet on Canvas in the resources folder. You can try to challenge yourself and figure out if you can guess what the last term of each of these electron configurations would be based on the little trick that I just told you. So what energy level is it in? What period? What block is it in? SPDF. And how many elements into that block is it? 1 through, we're really going to go up to like 10. We're not going to go into the F block very much. Okay, so practice these ones and then you're done so with this note set. Yay!